our topic is oscillation and wave motion. So learning outcomes, define vibration, describe and apply simple harmonic motion, relate energy and speed in such systems, classify types of wave phenomena, describe the motion of a simple pendulum, solve simple problems for a simple harmonic motion. So, topic outline is type of waves, properties of waves, concept of sound, simple harmony. So, it's a video of a oscillation, or we call it catching a wave. It's an experiment. So, we can see that the guy is holding a fabric and a wave occurs when the fabric is back from its equilibrium position and the energy is transferred down the fabric. When the wave reaches the end of the fabric, it bounces back, similar when the sound wave hit a barrier and creates an echo. So the guy is trying to race with the fabric. So if you pull the fabric tighter, the wave travels faster. This is because the higher tension in the fabric, the higher the restoring force. And the faster the fabric reacts to send the wave on its way, we can see that this is the relationship between tension and wave speed by trying to win the race. So next, here's another experiment, which is a clear demonstration of constructive and destructive interference of a two waves in a string. So this is a destructive interference wherein there will be no wave at all. And the next interference is constructive interference wherein they will create a large wave or bigger wave. So if each wave is pushing the string on the opposite direction when they meet, the string is not displaced from its equilibrium position at the meeting point. However, if both waves are pushing the string in the same direction, the string's displacement from equilibrium is larger than it would be only if one wave was present. In either case, both waves emerge unaltered and traveling in the same direction they were before the interaction. Next is another experiment. They put a water inside the balloon. Then there will be a lot of waves not gonna happen at the same time. So this is another demonstration of constructive interference wherein they will create a huge wave. But this time there is a lot of waves that have meet at some point. So next, here you can see this guy is holding a trumpet and he will demonstrate a sound wave. And of course, when there's no way we can see sound wave, so we will put a bubble to show its vibration. So he is playing the note, and we can see that it is creating a vibration. And the sound wave passes right through the bubble, and it causes no what do you call that, disruption at all. But since the bubble is so fragile, it is easily popped. So next, repeated back and forth movement of something between two position or state. So like what we saw in the video earlier, there is the first video, catch the wave. The guy uh, inserts some tension on the cloth and then it went back and forth. So these occur around an equilibrium point or mean value. A single oscillation is a complete movement no matter what direction. Next. So basic concept of oscillation, complete back and forth movement of the oscillation body is called a period. The period duration T is the time needed for an oscillating body. The amplitude is the extent of a wave measured from the highest peak down to the zero position. Frequency is the quotient of the number of periods and the time required for it. Elongation defined as the current distance from the zero position. Circular frequency is the angular velocity of the circular movement whose projection on a straight line result in a harmonic oscillation. The phase is specified by the two oscillation parameters, elongation and time, and is indicative of the current state of oscillation. The damp oscillation is an oscillation in which the amplitude of the oscillating quantity decreases with time because of frictional forces. Undamp oscillation have constant amplitude. It is necessary for the energy supplied to the vibrating system to be maintained in the case of constant small energy uses. A sustained undamped oscillation in reality is only approximately possible. In order to create a real undamped oscillation, the energy uses that must be compensated by a regular energy supply. So this is a wave. So a wave is a spatial and temporal periodic process. They are usually perpendicular to the wave ray runs the wavefront. The wavefront is the geometric location of all the particles that belong to the same phase. The distance between two successive wavefronts is called the wavelength. The distance between two neighboring particles of the same oscillation phase is the wave propagation, which is independent of location and time. The wave propagation can be analyzed according to Huygens principle of wavelengths. In this principle, every point of a medium covered by a wave motion can be regarded as the starting point of a new wave, a so-called wavelength. So next. So this is the crest, the top of the wave, and the shore is the bottom, and is the rest position, or we call it a median or region, the middle part, and this is the distance. Next, so this is from here, from this rest up to the top, to the we call it the amplitude, and from this top, from another top is called a wavelength. So properties of wave, amplitude of the wave is a measure of the displacement of the wave from its rest position. Measure of the strength or intensity of the wave. Wavelength of a wave is the distance between two corresponding points on the back to the back cycle of the wave. So can be measured between two crests of a wave or two shore of a wave. The unit is called lambda. Properties of wave. Frequency of a wave is the number per second of a wave cycle. So ilang beses siyang nag-wave. This is measured in hertz or cycle per second, and its unit is hertz. And period of the wave is the time between wave crests. This is measured in time units. Properties of wave, speed or velocity of wave. Another important property of wave is the speed of the propagation. This is how fast the disturbance of the wave is moving. The speed of mechanical wave is traveling through. So From here to there is the t, and also here is the time. So to get the omega is equal to 2 pi over t. Frequency is equal to 1 over t. One cycle described by 2 pi regions of a phase. Omega is equal, the angular frequency is 2 pi, 2 pi multiplied by frequency. So next is 45. Then its equation is, the radius is pi over 4. And 90 is pi over 2, 135 is 3 pi over 4, 180 is pi, 225 is 5 pi over 4, 270 is 3 pi over 2, 315 is 7 pi over 4, 360 is equal to 2 pi. So, next. The oscillation process is an extended medium is called oscillating wave. The extended medium consists of a vast amount of oscillating particles, all of which are interconnected. If one of the particles receives an oscillation impulse, then it becomes the center of the propagating wave movement. But no matter is transported, the direction of energy propagation is called the wave rate. Each wave front conforms to the envelope of wavelets. Huygens principle applies to all types of waves, even electromagnetic waves. So next, three types of waves. So the longitudinal waves, the particles oscillate the back and forth in the direction of propagation. If particles oscillate in the direction of travel of the wave, and overpressure occurs. If they oscillate opposite to the direction of their travel, a vacuum occurs. Compression and rarefaction alternate. So this takes example of longitudinal wave. Then next is transverse wave. The particle oscillate perpendicular to the direction of travel of the wave. Transverse wave have alternating trough and crest. So this is the example of transverse wave. And as you can see, there is a alternative, what do you call this, trough and crest. So surface waves are two-dimensional waves. They propagate in an expanding surface. So this is the surface, and this is the sky wave. This is three-dimensional. They propagate in the form of an expanding sphere. So when the surface wave have a functiform excitation center, the wavefronts are circles. When the sky waves have a multiple excitation center, the waves are spherical shells. The velocity of a wave propagation c is equal to the production of the frequency f, with which each particle of the wave oscillates, and its wavelength, or we call it lambda. The velocity of wave propagation is equal to the product of frequency f, which each particle of the wave oscillates, and its wavelength lambda. So c is equal to frequency multiplied by lambda, or the wavelength. The velocity of wave propagation is given by the following equation. So this is the elastic transverse wave, which is in solid. So c is equal to f over t, and this is the elastic longitudinal wave in solids. C is equal to the square root of E over T. And longitudinal wave in liquids is C is equal to square root of K over P. So, where C is the propagation velocity, F is the tension force, A is the cross-sectional area, B is density of the medium, E is the modulus of elasticity, and K is the Bird modulus. If two waves superpose and succeed in amplitude frequency, the wavelength but run in opposite direction, a so-called standing wave occurs. In a standing wave, the spatial image does not travel any further. Location at which the amplitude is maximum and location at which amplitude is minimum or equal to zero remain in a constant position. Standing waves can vary with the reflection in a thinner or a denser medium. A standing wave occurs most frequently when a plane superposes with itself reflection. So, what is reflection? Reflection is when a wave strikes the boundary of its medium onto another medium which is entirely a partially reflected. So, process is called deflection. The law of reflection as it follows is angle of incidence is equal to angle of reflection. So, angle of incidence is a, what do you call this? Its symbol is A while the angle of reflection is beta. So, a wave ray is refracted during a transition between two media and the propagation direction and the propagation speed change. For the propagation velocity, the law of a refraction applies. Sine, sine angular and sine beta is equal to C1 over C2. So, diffraction. Further change in the propagation velocity of the wave can be found at the edge of the obstacle such as a slit. So, here is the slit. And the obstacle does not cast sharp windows. In Huygens' principle can explain the phenomenon of diffraction as shown below. The energy of the wave particle refracted through opening slits of the wall is distributed in the individual direction after diffraction so that the energy part decreases with increasing diffraction angle. The diffraction angle is the angle between the original wave direction and the new wave direction. So next is simple harmonic motion. Any motion that repeats itself after a certain period is known as a periodic motion, as I have said earlier. And since such a motion can be represented in terms of sines and cosine, it is called a harmonic motion. So simple harmonic motion are say the following example. So a test tube bobbing up and down in water, a simple pendulum, a compound pendulum, a vibrating spring, atoms vibrating in a crystal lattice, a vibrating salt river, a trolley fixed between two springs, etc., etc. Next, this is the characteristic of simple harmonic motion, so repetitive motion to a central equilibrium point. System of maximum displacement, period of each cycle is constant. Force causing the motion is directed toward the equilibrium point minus sign. F directly proportional to displacement toward equilibrium. Acceleration is equal to omega squared times displacement or the angular velocity. Sorry, angular velocity squared times displacement. So the Lagrange digital variation displacement with time for oscillating mass in a string. Process is data to find the velocity and acceleration with time. Now use the data to obtain a graph of acceleration versus displacement. So in analyzing the graph, you need to find the time period and the frequency, amplitude, the value of velocity at maximum displacement, the value of acceleration at zero displacement, the relationship between displacement and acceleration. A free body diagram for SMH drawing a free diagram for the mass when it comes meets in the center of the motion, at the top motion, between the bottom and the middle down, and between the bottom and the middle heading upwards. So superposition of isolation. Each oscillating system can execute several oscillations simultaneously. The individual oscillation overlaps and form a resultant oscillation. In conclusion, if the oscillating bodies execute several oscillations, then they superpose themselves without interfering with each other. A distinction is made between oscillation that possess the same oscillating direction and oscillation whose direction of oscillation are perpendicular to each other. Simple harmonic vibrations with the same direction and the same frequency are superposed What results is harmonic oscillation at the same frequency. So this can also be symbol the term as sine and cosine. So the pace of the initial oscillation also affects the amplitude of the resulting oscillation. When two oscillations in the same direction but not the same frequency are superposed, the result is non-harmonic oscillation. So damp oscillators. So damping usually comes into play whenever we consider motion. We study the effect of a spring mass system. The damping force is assumed to be proportional to the velocity acting to oppose the motion. So total force acting of the mass is frequency is equal to negative kx minus cx. The motion for damped spring mass is mx is equal to negative kx minus cx. By casting in a convenient coefficient, x is equal to 2 beta x plus w 02 x is equal to 0. This is second order homogeneous equation with constant coefficient. Both w subset of 0 and beta have dimension time quantity power in the power of negative 1. Here, 1 over W is the time scale of the oscillation that would occur if there is no damping. And 1 over beta is the time scale required for damping to bring any motion to rest. It is clear that the nature of the motion depends on which time scale 1 over omega 0 is equal to, or 1 over beta is larger. So the trial solution is x quantity p is equal to a e the power of a t. So quadratic equation is a squared plus 2 beta a plus w squared is equal to 0. The nature of the solution depends critically on the value of the damping coefficient beta, and the behavior is quite different depending on whether beta is less than w subset of 0 or beta is equal to w subset of 0 or beta is equal greater than w subset of 0. Under damp, this is the condition in which damping of an oscillator causes it to return the equilibrium with the amplitude gradually decreasing to zero. System returns to equilibrium faster but overshot and crosses the equilibrium position for one more time. We first consider a situation where beta is less than W, which is referred to the undamped defining W is equal to square root of 0, square root of W 0 to minus beta squared. The two roots, which are both complex, have values a subset of 1 is equal to beta plus IW and a subset of 2 is equal to negative beta minus WI. Resulting solution is a superposition of the two roots. X quantity p is equal to a to the power of beta p, quantity a times e to the power of iwt plus a subset of 2 is the power of negative wit. So where a subset of 1 and a subset of 2 are constant, which have to be determined from the initial condition. The term a subset of 1 is so this equation is a superposition of sine and cosine, which can be written as this. This can also be expressed in a complex notation, which is this, where where is a is equal to I to the power of I. Null is the complex amplitude, which has both the amplitude and phase information. Uh, this uh, this image shows underdamped motion, and the equation is x quantity p is equal to e to the power of negative p cosine quantity 2 pi multiplied by p. In all cases of damping reduces the frequency of the oscillation. W is less than WO. The main effect of damping is that it causes the amplitude of the oscillation to decay exponentially with time. It is often useful to quantify the decay in the amplitude during the time period of a single oscillation. T is equal to 2 pi over W. This is quantified by the logarithmic decrement, which is defined as lambda is equal to logarithmic of x quantity t over s quantity t plus t is equal to 2 pi beta over W. So, overdamp harmonic, and the condition in which damping of an oscillator causes it to return to equilibrium without oscillating. Oscillator moves slowly towards equilibrium than a critically damped system. This refers to the situation where beta is greater than W. So, the two roots are A is equal to negative beta plus square root of beta to the power of 2 minus W squared is equal to negative lambda, and A is equal to negative beta plus square root of beta to the power squared minus W2 to the power of 2 is equal to negative lambda, where the both lambda is greater than 0 and lambda 2 is greater than lambda 1. The two roots give rise to exponentially decaying solution, one which decay faster than the other. X quantity t, or the constant A, and A2 are determined by the initial condition for initial position x and velocity v. We have x quantity t is equal to velocity 0 plus lambda 2 multiplied by x0 all over lambda 2 minus lambda 1 multiplied by lambda 1 multiplied by t minus velocity 0 plus lambda 1 multiplied by x0 all over lambda 2 minus lambda 1 multiplied by e to the power of lambda 2. So this is the overdamp oscillator does not oscillate. Beta is greater than W0. So this is the equation, and we have lambda 1 is equal to W2 multiplied by 2 beta, and lambda 2 is equal to 2 beta. Critical damping. The threshold between overdamping and underdamping. In the case of critical damping, the oscillator returns to the equilibrium position as quickly as possible without oscillating and capacitance once appears. This corresponds to a situation where beta is equal to W, and the two roots are equal. The governing equation is in second order, and there is still no interdependent solution. The general solution is x quantity t equal to e to the power of negative beta t quantity a plus a multiplied by t. The solution x quantity t is equal to x e to the power of negative beta t quantity 1 plus beta t is for oscillators starting from the rest at x0, while xt is equal to v velocity 0 e to the power of negative beta t is for particles starting from x is equal to 0 with speed v0. So, oscillator and external force. Considering an oscillator under influence of an external sinusoidal force F is equal to cosine quantity Wt. This is because this is merely an arbitrary varying force. Ft can be decomposed into the sum of sinusoidal forces of different frequency. So this is the solution. So here F and respectively the amplitude and phase of the different frequency components such as expansion is called a Fourier series. The behavior of oscillator under the influence of force F quantity T can be determined by separate solving. So this is the solution for solving the um, the behavior of oscillator under influence of the force. So next, for a force with a single frequency and the superposing of this solution, x quantity t, so this is the single frequency. Then next solution is for sinusoidal forces or single frequency, wherein and for the complex notation, and this is much more convenient than this, so we're gonna use this what do you call this equation, wherein f is equal to I over m. Next, so complementary function and particular integral, the solution is a sum of two parts. The first term is called complementary function, is a solution to equation without this is the solution without external force. With the oscillates at natural frequency of the oscillator, this part of the solution is exactly the same as when there is no external force. This has been discussed extensively earlier, and we shall ignore this term in the rest of the chapter. So the second term, this term called the particular integral, is the extra ingredient in the solution due to the external force. This is isolated at the frequency of the external force. X plus W is equal to F e to the power of I W, which gives quantity negative W squared plus W B is equal to F, whereby the solution is this, and the amplitude phase of the dependent forcing frequency. The amplitude is this is the equation how to get the amplitude, and to get the phase of oscillation with a applied force is this equation. The first point to note is that the amplitude decreases dramatically at W0, and the amplitude low at W is equal to 0. This is phenomenon of resonance or the resonance. The response of the oscillator is maximum when the frequency of the external force matches the natural frequency of the oscillator. In real situations, the amplitude is regulated by the presence of damping, which ensures that it does not blow up to infinity at W is equal to W0. We next consider is the low frequency behavior, and is the solution. The oscillation of the amplitude F over K are in phase with the external force. This behavior is easy to understand if you consider W is equal to 0, which is a constant force. So 0 is a constant force. We know that the spring gets extended, contracted by the amount of X is equal to F over K. So in the direction, the same behavior goes through if F varies very slowly with time. The behavior is solely determined by the spring constant K, and this referred to as stiffness control regime. So next is the high frequency. So this is the solution, and the amplitude is F over M, and the oscillation are negative pi out of phase with respect to the force. This is the mass control regime. This is where spring does not come into the picture at all. It is straightforward to verify the equation in the solution. So when the spring is removed from the oscillator, interestingly, such particle moves exactly out of phase. Relative to the applied force, the particle moves to the left when the force acts to the right, and vice versa. So this is the effect of damping. Introducing damping, the equation motion. This is the equation. So here, again, we separately discuss the complementary function and the particular integral. The complementary integral function are the decaying solutions that arises when there is no external force. These are short-lived transient, which are not interested in studying long-term behavior of oscillation. These have been already discussed in considerable detail, and we do not consider them here. The particular integral is important when studying the long time or steady state response of the oscillator. The solution is this. The solution on the previous slide can be written as this, where null is the phase of oscillation relative of the force. So, to get the amplitude, this is the equation, and the phase is this. So, in this image, the amplitude and phase is a function of W for different values of the damping coefficient theta. The damping ensures that the amplitude does not blow up at W is equal to 0, and it is infinite for all values of W. The changing phase also is more gradual. The low frequency and high frequency behavior exactly the same situation without damping. The changes due to damping are mainly is vicinity of W is equal to W. So the amplitude is maximum, and this gives a solution for getting maximum. And for mild damping, this is the solution to get the W. So next is the response of external force performing peak of resonance only when beta is less than the mild damping limit. This is the great utility in modeling the phenomenon of resonance, which occurs in a large variety of situations in the weak damping limit. W peaks at W level 0 and falls rapidly away from the peak. The consequences we can use is this equation, which gives this. In the vicinity of the resonance, this is a maxima, and the maximum value is, and you will get the maximum value using this equation. We next estimate the width of the peak of resonance. This quantified using FWHM, or full width at half maxima, defined as full width at half maxima is 2 delta W, where A quantity C W plus delta W is equal to A max over 2. So half of the maximum, and to get the half of the maximum value is gonna use this equation. So we see that delta W is equal to delta F, and full width at half maxima is equal to 2 beta as shown in the figure. So this is and FWHM quantifies the width of the curve, and it records the fact that the width increases with the damping coefficient beta. The peak described by the equation above is referred to as a Lorentzian profile. This is seen a large variety of situations where we have resonance. So we finally consider the power drawn by oscillator from the external force. The instantaneous power P quantity T is equal to F quantity T x T has a value of this equation, and the average power of the quantity interest. We study this function. And to calculate this, we're gonna use this equation. So resonance. Resonance occurs when the excitation frequency matches the natural frequency of the oscillation. When the damping is small, the amplitude decreases greatly. In everyday life and in technology, resonance plays a vital role. So since every day we are using technology, so resonance is always there everywhere. Because most mechanical structures are subject to an oscillating force, they can be stimulated by external periodic forces. In the case of resonance, this would result in an increase of amplitude followed by the destruction of the structure. To prevent such a resonance catastrophe, one has to avoid any periodic forces or maintain large margins between the natural frequency and the excitation frequency, provide damping options, and allow the resonance frequency for only a short time, a time that is less than the build-up time. For rotary movement, the resonance frequency is referred as a critical functional speed. So next is electrical circuit. Electrical circuit are the most common technological application where we see resonances. So, as mentioned earlier, resonance is part of the technology. So, electrical circuits have a resonance. So, the image is what we call LCR, characterize the typical situation. The circuit includes a signal generator which produces an AC signal of voltage amplitude at frequency. Applying Kirchhoff's law to the circuits, we have this equation, and which may be written solely in terms of the charges Q as this. So next, we see that this is a damp oscillator with external sinusoidal force. The equation governing this is this equation, where W is equal to 1 over LC, beta is equal to R over 2L, and V over L. The next consideration is the dissipated in the circuit. The resistance is only circuit element which flow powers. We proceed to calculate this by calculating the impedance, which this equation, which varies frequently. The voltage and current is related to the which give the current, and to get the current is this solution. Next is Raman effect. The light of frequency incident on a target. If the emerged light is analyzed through a spectrometer, is found there are components at two new frequencies known as the stroke and the anti-stroke line respectively. This phenomenon was discovered by Sir C.V. Raman and is known as an example, we consider light frequency V equals to 6.0 times 1014 Hz incident on a beam which is a liquid. It is found that there are three different pairs of stroke and anti-stroke lines in this spectrum. It is possible to associate each of these new pair of lines with a different isolation of the benzene molecule. The vibration of a complex system like benzene can be decomposed into different normal modes, each of which behaves like a simple harmonic oscillator with its own natural frequency. There is a separate Raman line associated with each of these different modes. A closer look at these spectral lines shown them to have a finite width, the shaping corresponding to the resonance of a damping harmonic oscillators, and in this figure shows the Raman corresponding to bending mode of benzene. So next is electromagnetic waves. So what is light? Particle or wave. Much of our daily experience with light, particularly the fact that light waves move in straight lines, tell us that we can think of light as a stream of particles. This is further borne out when placed of opaque object in the path of the light rays. Sa electromagnetic spectrum, the electromagnetic wave is caused by the oscillation of coupled electric and magnetic fields. They are dependent on the frequency. Electromagnetic waves can be propagated both in free space and in vacuum. They do not need a carrying medium in a vacuum. These waves propagate at the speed of light. The speed of light in a vacuum is, according to current measurement, is c is equal to quantity 299,792.5, positive negative 0.9 km per second. So next, so infrared light, the white light of an arc lamp or light bulb provides invisible radiation that can be found in a visible spectrum. Next to red, it is referred to as infrared radiation and results in infrared light. Ultraviolet light. The ultraviolet color range lies outside the violet range of the visible color spectrum. Irritation and tanning of the skin by the sun are due to the ultraviolet light component. Mercury vapor lamps that are used to artificial tanning lamps also emit ultraviolet light. The different impression of colors are projected to our eye by different frequencies of a visible spectrum. So next, gamma radiation. Apart from the nuclear components, protons, neutrons, and electrons, today, more than 200 other elemental particles are known. Many of them are the result of interactions between terrestrial atmosphere and cosmic radiation, the product of nuclear disintegration of particle accelerator. Most of the elementary particles exist with the antipole electric charge and the reverse magnetic momentum, and these are called so-called antiparticles. If a particle meets with the antiparticle, the result is annihilation. The energy of annihilation is released as gamma radiation. Next is sounds. Uh, Everything perceived with the human ears is called sound. We distinguish between tones and noises. The way we perceive a sound event depends on its volume, pitch, and timbre. Sounds come from a sound generator, which is oscillatory body. In order for sounds to reach our ears, it must be transmitted by a sound carrier. The propagation of sound requires a solid, liquid, or gaseous body of a sound carrier. Sound cannot be transmitted in a vacuum. The sound source generates progressive longitudinal waves in the sound carrier. The perception of sound occurs when these longitudinal waves reach our ears. Speed of sound. The speed of sound specifies how fast the sound propagates in a particular sound carrier. It is independent of frequency in the air. For example, the speed of sound is 40 per second is in water, and in water 1,440 per second. When sound waves hit another medium, they are reflected at the transition boundary. Sound waves. Sound waves are mechanical longitudinal waves. They have their origin in the sound source and propagate in solid, liquid, or gas in the form of compression waves. Example, the human ear can hear frequency from 16 Hz to 20,000 Hz. Frequency lower than 16 are called binaural sounds. Frequency higher than 20,000 Hz are called ultrasounds. In acoustic distinction are made among the following types of sounds. Tone. The pure tone is graphically displayed in sinusoidal waves. The frequency specifies the pitch of the tone. The ratio between two tones is called the interval. In musical intervals, the lowest tone is called the root of fundamental tone. The higher notes are the octave. The perfect fifth and the perfect fourth, etc. The musical interval of two tones, which can be detected by the sense of hearing, is defined by the quotient of their frequency. Sound. Several sinusoidal oscillations superpose to a non-sinusoidal vibration. The pitch is determined by the root. The other sound convey the timbre. Noise. A variety of sounds with rapidly changing frequency and strength, and bang, a sudden loud noise that lasts for a very brief time. And that's all. Thank you.